Hi guys, it's nice to be here. I'm not that used to giving talks, so we'll see how it goes. But my name's Declan Doherty. I am a software engineer at Orbit, which are an Italian-based space services and space infrastructure company. I've just realized I forgot my clicker. So I've been working there for the last sort of 4.5 years, and I'm going to talk about operating compute nodes in space, essentially, and the challenges of that. So just to start, I'm just going to run through some terminology which totally confused me when I started working in the space industry, and still kind of does sometimes. But I might talk about some of these concepts. So a CubeSat is basically a small satellite and a standardized size and shape. And then a payload is something that's transported on a satellite, for example, a camera or an antenna. Hosted payload then is kind of something custom to deorbit based on the systems that we use, which I'll show in a minute in the next slide. But a hosted payload is something that stays on the satellite after we launch and shares resources for example, power and communications. Then a mission is a single defined goal or operation. Mission controls the software and processes we use to manage satellites. And then there's different types of orbit, LEO, MEO, and GEO. So I'm really talking about low Earth orbit, which is LEO, because that's currently where we operate our compute nodes. So one of the key innovations that Orbit came up with was this ION spacecraft platform. And it is a spacecraft in the sense that it has its own thrusters and it can maneuver in orbit and sort of change its position and attitude. And you can kind of think of it as like a mothership for customer CubeSats and all our payloads. So the customers can provide us with their CubeSats and we can load them onto our launcher. Our launcher goes on the rocket, and then once it hits low Earth orbit, it can position the satellites for our customers in whatever orbit or attitude they required. So, and it's not just a single satellite; it's actually a product line. So the picture on the right-hand side here is just 3 IONs currently being manufactured, and we launch these at a regular cadence, like at least several times a year or more. This clicker will work. There we are. So on those IONs, we have obviously compute infrastructure, compute nodes. Obviously, there's a computer that controls the satellite, but then we have all our processing capabilities. And so after we've deployed satellites, we can reuse that for all our purposes. So some of the use cases that we use that for is mostly in real-time data processing and alerting in likes of Earth observation. So things like infrastructure monitoring or wildfire alerting, this kind of first responder kind of task. And then dynamic tasking is like when you have multiple satellites, deciding which satellite is appropriate for a given task based on its properties or its orbit. And then space domain awareness is more about, instead of observing Earth, observing the space environment, checking for objects or checking for potential collision detections. So obviously a lot of this stuff is still research-based and experimental, but we're starting to see more and more commercial use cases. So operating compute in space is a wee bit different than on ground because you've all these other challenges that you don't normally think about. So for instance, we've got radiation, and that can corrupt your data or damage your components. So you have to think a bit more about defensive programming techniques. For example, you could have, say, a piece of code with a variable that's set, and you're working in a loop, and you're expecting this variable to be whatever value, and then somehow a bit gets flipped and it's corrupted, and you end up in an infinite loop, or your system crashes or whatever. So radiation's a big thing. Same as thermal control. So we don't have any convection cooling. There's no fans. So all the heat dissipation is managed by more or less infrared radiation. So you're kind of bolting heat sinks to things and bolting the computer and heat sinks to the frame of the satellite, this kind of stuff. And then obviously the big thing is your hardware can't be physically accessed. Once it's deployed, that's it. You can't get your hands on it physically. So these other 2 big constraints for us that really impact us, I guess, is connectivity. So in low Earth orbit, generally speaking, we have very limited contact windows. So obviously the satellite orbits the Earth, and as it does that, it passes over different ground stations, which are usually owned by other third parties, and you kind of have to book passages of connectivity. So you have to know where your satellite is and then book those passages often in advance. And with that, you can have constrained bandwidth depending on the radio equipment that's on the satellite. So traditionally, that would be S-band or X-band radio. So you could be talking a few kilobits per second to a few megabits per second. And then power is a big constraint. Obviously, with a hosted payload, like which we are with our compute nodes, we're sharing power and communications with the platform. So obviously, critical systems that maintain the satellite's orbit have to kind of take priority. So you can't actually always assume that your compute node is powered on. So sometimes you'll have to schedule powering on the compute to do some processing. And sometimes you'll have to delay that because there are other critical systems or the batteries need to be recharged, which can only happen when the solar panels are in direct sunlight. So for part of the orbit, the satellite will be in the Earth's shadow. So there's all these kind of constraints around when you can run your computer and what you can do. And obviously you've got limited debug access because you can't get your hands on it. So what that means is your kind of traditional assumptions that you will have on ground when you're operating stuff will kind of break. So obviously on ground, for better or worse, we usually assume the network's available. But as we've seen, that's not always the case with satellites. It's usually quite easy to redeploy stuff when it breaks on ground, but sometimes that's not always an option. And observability is a massive thing. So on ground, obviously, you can continuously observe stuff, but in space, we're relying on telemetry, which is delayed, or sometimes, it's only partial. So it's quite difficult to debug. So traditional space systems kind of tackle these issues in a way to kind of minimize risk and minimize uncertainty as much as possible. And that was obviously because launches were really expensive. They were really risky. Things could blow up. You had to spend a long time planning and developing your hardware and your software for your specific mission. So it was that specific task. And that was what everything was sort of built around. There was no thought or concept of maybe repurposing the satellite after launch. So systems were tightly coupled, your software and your hardware. So your software maybe knew a lot about your hardware, specific timings. Obviously, a lot of that stuff's still true for flight software, but essentially it was a very narrow mission focus, usually with limited onboard compute and a small number of spacecraft, because with all the complexity, the more spacecraft you add, it gets harder and harder. But space is changing. And the reason it's changing is, I guess, the launch capabilities that we've sort of seen happening in the last sort of decade or so. You can see this graph from ESA in the top right shows an explosion in launch from around 2020. And it's important to note it's actually commercial launch, so it's not like military or defense or whatever. It's commercial launch has really taken off. Pardon the pun. There might be a few of those. Anyway, but that means then that your satellite counts are increasing, your payload counts are increasing. We're getting more and more stuff up into low Earth orbit. And alongside that, we're seeing a fast development pace in compute performance and the stuff that we can actually put up there. Shorter timelines to do that, and a more diverse array of communications technology. So like K-band radios for greater bandwidth, optical links, again, for greater bandwidth, and LEO mesh networks, so intersatellite connectivity. That's becoming sort of starting to take off. Again, another pun. And geostationary data relay, things like Iridium satellites, so you can connect from your low Earth satellite to geostationary to give you like a more permanent connection. And we're also seeing the concept of software-defined missions, where we're redefining what the satellite does for a purpose that maybe we didn't think of before we sent it up, but it has certain capabilities that maybe it could be used to accomplish a different task. And of course, with all this launch, all this stuff going up, we're talking about fleets instead of like a single isolated spacecraft. So the challenges are there, and things are changing. So where this comes as a cloud native, I'm getting there. So sorry, I'm going to take a drink of water. Throat's dry. So with more capable onboard processing, we can start to think about using more diverse operating systems. That can, of course, I'm talking about Linux. That brings mature tooling that's been battle tested in the cloud over the last couple of decades. We rely on it. It's reduced dependency then on our bespoke custom proprietary stacks, but also it's a more accessible development platform. So you can start to think about potentially running stuff that you would normally run on ground in orbit. And you're making, potentially making space application development more accessible to all our developers, not just some siloed set of specialist flight software engineers. And so this is where comes the cloud native. We're obviously talking about increased compute, trying to run ground software in orbit, and trying to do this like not with a single machine, but 10 or hundreds. So it's the scale. And obviously cloud has been solving the problem of scale for the last nearly 20 years. And there's been a lot of lessons learned, a lot of stuff developed. So it's not necessarily about, okay, we can put Linux, we can put more advanced compute in space, let's put Kubernetes and just go. It's more about what can we learn? What lessons can we learn from how cloud native approaches deployments and management of systems and operations? And it's things like declarative desired state. So saying, describing how you want the system to behave rather than the steps of how to get there, and then using reconciliation loops to monitor the current state and try to bring the system up to the desired state. Automated recovery, obviously, if we can't put our hands in the box, then the system needs to be able to fix itself and detect an error and fix that without a human in the loop. And policy-based deployment is a big thing because we have a diverse array of hardware with different sensors, and we're developing applications. We need to make sure that they go to the right environment. So how do we do that without manually babysitting everything? And then obviously containerized applications. So containers were the key enabler and are the key enabler for cloud. And we're kind of seeing that now in the work we're doing in orbit. It's really, we're starting to reap the benefits of being able to, package our workloads more consistently. So we know when we test something on ground, it's a more high degree of confidence that when we put it in orbit, it will work. It gives us some degree of application isolation, so we can start to think about running multiple services on shared compute at the same time. And obviously a big thing is we can uplink layers independently, so we can even preload the satellite before launch with base images and then just upload the diff. And that obviously saves us a lot of uplink bandwidth, which is one of the key constraints. But we haven't been operating in a vacuum. It's another one of those puns. Just as cloud's been solving the issues of scale, a lot of parallels in edge processing and IoT domain have also been sort of similar to the challenges that we see in space. So often they're trying to operate diverse hardware stacks in harsh environments with potentially limited connectivity. So there's loads of stuff, there's loads of work, loads of frameworks, loads of tools that have been developed. So it's impossible to talk about them all. But I'm just going to give a quick overview of two that I think are very interesting, and which we've kind of prototyped stuff with. And it's really about how they're tackling the challenges from different angles and how you can combine these tools to kind of make custom solutions. So the two frameworks are EdgeX Foundry and Open Horizon, and they're both Linux Edge Foundation projects, so they're sponsored by the Linux Foundation. So EdgeX Foundry is the first one. It is essentially for figuring out how to build software for nodes that are very diverse, different types of hardware, different types of sensors, and do that in a kind of standardized way. It describes itself as edge middleware. It supports a wide array of devices, and the key thing is it defines these common data schemas and common APIs, and it works with a concept of a layer of containerized services. So the blue layer you see there is like the core services, which is like really for managing the data that's ingested into the system and for managing the understanding of the configuration of what devices are available, what applications are installed, etc. And then they're supported on either side by device services for wrapping specific pieces of hardware. and then supporting services like a rules engine that lets you stream data in a SQL kind of language and then trigger scheduled workloads or notifications, etc. But the device service is kind of what I'm going to focus on here for this. There's so much to this again, but essentially there's a pre-existing set of device services for all sorts of standardized hardware. So things like USB cameras and, Modbus, which you would see in manufacturing a lot. But even REST or MQTT, if you want to think about interacting with an external system as a data source or a device. But if you have a custom piece of hardware that you need to develop a device service for to bring it on board to EdgeX, they make it quite easy with their SDKs. So they have SDKs in Go and C, and I think Python as well. So in order to bring a hardware device into EdgeX, all you really have to do is define a device profile, which is just a YAML file describing the data types that your device reports and whether they're read and write or read only, etc. And then implement this kind of pretty simple interface using their SDK around your device driver. So this is just an example of like how to handle a read command for that device, and that means once you create that device service, bring it up on an EdgeX environment, it can register itself with EdgeX just through a simple API, and the applications that are there can understand by querying EdgeX from your device profile, understand what type of data your device reports, and start querying that data, but also interacting and commanding that device automatically without obviously having to change or having specific knowledge of that device. So you can see here on the left, that is an API request at a device service, which it comes up, it sends to EdgeX and says, here I am, this is my device profile, this is my device service name, and you can listen on the API there at this port. And then that standardized API then can be used by higher level applications. And on the query there, you can see an example of that standardized data schema. So in EdgeX, it's a quite simple, there's a concept of an event, which is a point in time, and then a set of readings. And those readings are just your data reported from your device, and they adhere to that device profile as you defined earlier. So that's EdgeX in a nutshell. There's so much more to it. Don't have time to go into it now, but this is one of the key things about it that I really like. So moving on to Open Horizon. So this kind of takes a zoom out, and it has a different approach to solving the problems. It's not about the node, how to build the software for a node with a specific piece of hardware, but it's how do we manage tens or hundreds or even thousands of these nodes, because obviously that scale, how do you know what's deployed where, what needs to be deployed where, and that's what Open Horizon tries to tackle. So it actually started inside IBM, I think, and then they open sourced it under the Linux Edge Foundation. So it does what it does through a few concepts. One's the central management hub, where you create an application and you register that application with the hub, along with a deployment policy to say, okay, this is my app, it needs this amount of RAM, it needs this amount of CPU, but maybe it also needs, access to a certain type of data, or even a specific piece of hardware, a specific sensor. You can specify all that in the deployment policy. And then it has this agent-based policy-driven deployment for the node. So you can take a node out of the box, install the agent on it, point it to the management hub. So instead of configuring the agent or the node manually on the hub, the node makes itself available, and it publishes its own policy to the hub and says, look, here I am. This is some information about me. This is my architecture. This is some constraints I have. This is equipment, is available devices that I have. And then the central hub will compare it against its deployment policies for the applications it has and start to negotiate between the two of them to say, okay, maybe you're a good environment to deploy this application, so take it. And then the key thing then is that the node can actually do this disconnected. So I say disconnected, it obviously needs a connection to download stuff, but it can start to download the application. And if it goes through a period of no connectivity, it can wait till it connects again and resume where it left off, sending a heartbeat to the hub. So that means that from your centralized hub, you can get a view of all the nodes you have, whether they're online, what their deployment state is, what applications are running. So it's pretty powerful. And then you can start to integrate the central hub's APIs with your own software. So that's just a screenshot of our internal mission control software. So here is an example of what those policies look like. On the left, we have the node policy. So this is just describing, like I say, the architecture. It's AMD 64. It's already saying I have this version of this application. I have equipment camera. I have station greater than 15. And then the deployment policy on the right-hand side is the application policy. And you can see that the constraints it requires are station equal to 16 and equipment camera. So the hub will see that these policies kind of agree and maybe suggest to the node that it should deploy that application. So really what I'm saying, we're seeing this shift in the space industry from like bespoke systems and hardware-defined functionalities to more like reusable platforms, software-defined missions, redefining what the satellite does after launch, not before, and then fleet-scale operations from single missions. So more need for more autonomous management. And we're able to adopt with our increasing compute more open tooling and more open frameworks. And obviously, with this, then potentially we can open up space to more people. So just as launch capabilities were an enabler for easier and more simple and cheaper, less expensive access to physical space for companies to basically start putting stuff in orbit, we see cloud and space and the adoption of these open source tools and frameworks potentially making space as a runtime environment for software more available to software developers, to create more businesses, create more communities, create more potential. So it's really about taking space infrastructure and the cloud, expanding the cloud out so that the space infrastructure just becomes an extension of what the cloud is today. And in the future, maybe more and more people can start to develop apps and deploy them into space. I hope I'm on their time, but that's more or less it. So if we have time, I'm happy to take a few questions.
Thanks a lot for this amazing talk. Very interesting. Have an insight in something a bit more outside. Are there any questions for? Yes. Go.
Hi, thank you so much for such an interesting talk. So idea of sending Linux to space always seemed a bit counterintuitive. Might seem counterintuitive because Linux is a monolith, right? Mostly monolith. And if it's the kernel crashes, it crashes. So are there like any interesting anecdotes you can tell? How do you solve for it? Or like maybe this intuition is wrong altogether?
Any interesting stories? Not that I can talk about, but a point to probably make is like I just had this slide because I was going to include this and I thought no, it's not really relevant. It's probably not that interesting, but we're not talking about the ADCS control or whatever of the satellite with Linux. We still have a layer of platform which is responsible for the real-time control of the satellite. We're more talking about bolting on extra compute on top. So Linux is more for running data processing, machine learning, this type of thing, rather than actually operating the satellite. So we still have that layer below for the platform. And the point is that the compute sits above that and interfaces with the platform. So talking about potential things that can go wrong, that platform interface, when you want to update that is very risky. So if you do something wrong there, you can totally brick your compute node, hopefully without interfering with the control system of the satellite. But that would be one of the danger zones there, the platform interface.
Thanks. Any more questions? Yes, up there. I'll throw it.
We've seen that there's a major shift in security in terms of speed, right? That stuff needs to get updated faster and faster. And you said you now have interconnectivity and network meshes between satellites. How do you deal with this so that it doesn't become dangerous that, I don't know, nation-state actors start trying to control satellites and do whatever with it?
That's a good question. I knew somebody was going to ask that. I was like, okay, it's a really good question. So what we're doing is we do work with some inter-satellite connectivity more through geostationary links, and we do have our own custom, or at least third-party radios that we can start to get like HTTP IP connections and stuff over. So that's, I mean, how you deal with the security of that is like a whole other talk itself. In essence, like we do, so internally we have a team that we're developing to work specifically on this issue, to look at what the risks are. So it's a combination. Okay, we're learning how to operate the computing space. We need to learn how to secure it because it's it's a very attractive target. I think what we're seeing is that traditionally in commercial space anyway, there was very much the idea of security by obscurity. And that's obviously a bad scene, and it's out the window because these days, in theory, you can go on to AWS and with their ground station service, provision the ground station and start sending packets via radio to different satellites, or even go on eBay and buy some equipment and start sending packets or reading stuff from satellites. So I guess the point is it's not a solved problem. It's one that's ongoing. It's one that is its whole own area, but essentially we're moving away from this concept of, well, it's in space, nobody can touch it, but the reality is nowadays people can.
Fair enough, thanks.